Let's see, we are talking about limits. So we've done infinite limits, where in general, limits are asking for the behavior of a function. But depending on what the x value does in that behavior question, I handle it in a different way. So infinite limits are really horizontal asymptote questions. Are there any horizontal asymptotes? Does the function stabilize as I go far to the left, far to the right? How I handle that, yes, it depends on the function, but it's very different from finite limits. It has its own method. And in the case of a finite limit, where x approaches some specific c value, some number, it really depends on what this function is in relation to the x value in question. And the method is very different. This is really the horizontal asymptote question. Now, a part of this finite limit question could be a vertical asymptote question. Sure. For example, the limit as x approaches 2 of 1 over x minus 2. Sure. Because when we ask a vertical asymptote question, which we will in the future many times, we are asking, is there any indefinite growth in size of the y value of the function as x approaches a specific number? Now, we are keeping things very simple, excuse me, and contained. So the vertical asymptote question will almost completely be reserved for rational functions, and we are going to keep it as simple as looking where the denominator equals 0. So in this case, this limit does not exist because the denominator is going to approach 0. The form of this limit tells me when the denominator approaches 0, or as it's getting smaller and smaller, the top isn't doing the same thing. So there is no possible cancellation of that shrinking effect that could change the behavior of the graph. And if the numerator stays close to a non-zero number 1 in this case, and while at the same time the denominator shrinks down to 0, the whole y value, the fraction, whatever you want to call this, is going to approach some sort of infinity. There's no way around it. But something that might look similar doesn't have the same result. Let's say 2 again. Let's say one we've seen before. Oops. Just to sort of review, because I know yesterday doesn't have a video. Here I look at the form of this limit, and it's 0 over 0. And that doesn't reveal the answer right away, unfortunately, but it does tell me how to proceed. That there is simultaneous shrinking towards 0 of both the numerator and the denominator, which means depending how fast they change, I don't know what's going to happen. And that problem denominator doesn't necessarily control the behavior of the whole thing like it does in the first example. So the form still tells me, whoa, watch out, anything can happen here when they both behave the same, going to 0. So then I have a strategy. Well, it's the irrational function. So a good strategy next is to try and simplify by way of factoring. So I see the difference of 2 squares. So I want to see if that could help me find the function that behaves similar to the original, but is easier to look at. So by canceling the x minus 2's, I then see that the original function behaves the same as a polynomial, x plus 2, which doesn't have any problems, and I can easily find that it's a 4, limit exists, and so on. So in general, other things can happen that I am not going to really see often because they do feel like sort of special, slightly made up situations. But what's happening here is this graph, this rational function, because of what the two polynomials are, really looks like this, with a little hole at x equal to 2. So not all rational functions have that vertical asymptote bendy shape like the basic one. It really depends on what the polynomials in question are, and that then determines their interaction in the fraction, and things like that can happen. Where the original function isn't technically defined at 2, plug it in, you can't get an answer because you're dividing by 0. But the behavior is still stable and predictable, that if you walk along that graph closer and closer to x equal to 2, and I stop you and ask, which way are you going? You're headed to a y value of 4. You'll never get there. But as far as you're concerned, during the walking, it looks fine. Everything looks good. It's more of a technicality than a fundamental vertical asymptote property of this guy that I'll put over here, which is a shift to the right. There is a fundamental property in the function. When I approach 2, the y value blows up. Okay. So, let's explore this 1 over x minus 2 a little bit. Actually, let me zoom in on this graph right there. Oh, that's perfect. Look at that. So, I can't really say exactly what happens to the y value when x approaches 2. Because I see from the graph, which is a single transformation of the basic function, I know that's the graph, and I see that different things happen depending on which side of 2 I am. And if I want to really be as specific as I can, I can't leave it as general as this limit, because it just says I'm approaching 2 from around 2. Well, positive or negative infinity, I don't know. Yes, it's an infinity, it helps me, but I'd like to let me know which one. So we can expand the limit concept or refine it so that we can say a little bit more and be a little bit more specific. It doesn't change that we're looking at behavior. I just want to be a little bit more specific in saying as much as I can. So let me zoom in like this. So let's look at the function as an example. That's still fairly simple, 1 over x minus 2. And we can then say, okay, let's duplicate the graph here. Since we took an easy one, we can already visualize it. We know there's a vertical asymptote at 2. We know it behaves like this from our transformation experience. And we can then say, okay, well, let's say original, in its original concept, the limit as x approaches 2 does not exist. I do have y values around 2, but approaching 2 from around 2, different things happen. I need to know which side I'm on. So we could say we could be a little bit more specific. We could say as, let me go with it. If x approaches 2 from the right, now I'm limiting myself to not being around 2, but just coming at it from the right. Then my function approaches positive infinity. I'll leave a space here. My next sentence I'll say in words. If x approaches 2 from the left only, then I can be a little bit more specific and say my function is going to approach negative infinity. So I'm essentially splitting the original limit question into two pieces. Just the right side, just the left side. Because it enables me to be as specific as I can in my answer. Give as much information as I can. Now this sentence we're going to write in limit form. Limit, again, it's behavior. I'm looking at the same thing. But I'm going to refine that with x approaching 2. And then to indicate from the right, I'm going to put a little plus there above the 2. And then, of course, my function is over here. And then I can say which infinity it is. Still doesn't exist. Nothing has changed in the answer. I just want to be as specific as possible. I want to give as much information as I can. And to do that, I'm going to have to just come from one side to 2. Otherwise, different things happen. And I can't really say. So this we'll call a one-sided limit for obvious reasons. And it's just a refinement of the original limit concept. We're still looking at behavior, nothing has changed. But in some situations, by looking at one side only, I can give as much information as I can. The second sentence is then the limit as x approaches 2, but from the left, we're going to indicate that with a little minus sign at the top. Same function. That enables me, looking at the graph, to say, oh, if I just come at 2 from the left, the y value is going to grow in size. So the limit doesn't exist, but it's always going to be negative. So I can give as much information as I can. So we have these one-sided limits, which is really just a very small step to the side. It's not changing the concept, really. It just depends on the function and what I want to say. Let me zoom out a little bit. Any questions on one-sided limits? We'll do more examples, of course. So the concept doesn't change. It's just allowing me to be as clear and specific as possible. But it also allows me to handle other functions in a way that I should. If I look at the square root function, for example, we know what that graph looks like. It's one of our basic graphs. And if you are in any way not sure, there's no time like the present. Do not fall behind. As a side note, the danger of this course, I've said before, is that it deceives you. It puts you into a false sense of security with all its review and things that are familiar, and you think, I don't have to do much for this course, I'll do fine. And then slowly new things are introduced, and before you know it, you're far behind, and the second half of the course is an absolute disaster. It's really cruel in that way. But knowing it, we can prepare for it. Because the upside is that if I put in the effort in the first half, the second half is smooth sailing. So much easier. Because it's just a new spin on the same thing. Anyway, I can only give you the warning. It's up to you. We've said before the limit as x approaches 0 of this square root function doesn't exist. But why doesn't it exist? Very different reasons from the previous example. Why doesn't this one exist? Let me ask you an easier question. You can simply say yes or no. Do you know? I'm not going to ask you what. Whether you say yes or no, there's no follow-up question. Do you know why I say that limit doesn't exist? You have to know. I won't ask you. If your answer is yes or no, there's no follow-up question, but you have to tell yourself, yes, I understand why, because we've said this before, or no. And if the answer is no, you are not reviewing as you should. This doesn't exist because the original limit requires that I'm approaching 0 in this case, from around 0. Can you walk towards 0 from the left on the graph? There's no graph, I can't. There's a void of nothingness over here. So I can't examine the behavior if there is no behavior to examine. So it's a technicality, very different from this one. There was a graph I could walk on. I walk over here. Hey, I'm sliding down. I could do something. Here there is nothing to even look at. Same answer, different reasons. However, you can tell yourself and me that this is silly. There should be a limit. Right? The graph is pretty fine. There's no other half. It's not my problem. We could, however, say, I'll say it in words again. If x approaches 0 from the right only, then everything is fine. I'm going to squeeze it in. It approaches 0. That's the y value at 0. I can plug it in and everything. So you feel that, well, I can calculate a y value. Square root of 0 is 0. So surely there should be an answer to this limit question. This technicality is silly. And it is. We just need to refine the limit concept to not come at it from two sides. So I have my one-sided limit, x approaches 0 from the right, so that's a plus. Doesn't mean it's always positive, just from the right. Of my root function, and then everything's good, existing, perfect. So the one-sided limit allows me to not get caught up in technicalities where the behavior is fine. It's a basic function. It's just the technicality in the original limit that I don't really care about. I need to watch out for it, but I don't really want to stop at an answer of does not exist. It's a basic function. It should exist, but only if I come at it from the correct side. Oops. Any thoughts on that?
So basically it just exists on the right side.
There is no left. That's the problem. So we can easily have an answer that we feel we should by just saying, let's not look at a left side. And in this case, we shouldn't even look at a left side. There is no left side. But the original limit doesn't care. The original limit in its definition says I have to come at it from around the x value. In the case where I don't have both sides, I just restrict it to the one side I have a graph. So it's really not a big deal. And it's really a refinement that makes sense, I feel. But now that means you have to look out in the question. Do I have a two-sided limit? We'll call this a two-sided, no, not two-sided limit for obvious reasons. Or do I have a one-sided limit? I need to know. Because if I have a two-sided limit, I need to make sure that, first of all, can I come at the x value from both sides? Is the behavior the same from both sides? If I have a one-sided limit, then I can just ignore the other side completely. Let's see if there's an example. In problem 2.3, do I have space? Yeah, I have space for one. Problem 2.3. Ah, there's so many. I don't really know. No, this is mixed. 2.3. Let's start with something not too bad. What's the easiest? Let's go with number 11. limit x approaches 2 from the left, x minus 3 over x plus 2. Oh, that's silly. I'm going to change this. 11b. Because I'm going to do this 11 next. Just 11b first. Let's make it an x minus. I think that makes a little more sense. So I've changed the function. And we'll do 11 in a second. I'm going to do this one first. So whether I come at it from one side or both sides, the issue is still at 2. And I see this is a rational function. I still have an issue. I look at the form of the limit. Regardless if it's one-sided or two-sided, it's still the same question, pretty much. The form of the limit is -1 over 0. I like that because I have a non-zero number over a 0 in the form, and that tells me what the answer is right away. Sort of. Does it tell me something? It should. What does it tell me? Does the limit exist or not? It doesn't say, just don't be deceived. The answer isn't -1 over 0. That's undefined. It's more, they're approaching those numbers. And because the top one isn't a 0 either, only the bottom one shrinks down. This is going to be does not exist. It's going to be a plus or minus infinity. But I want to know which one. Because I have a one-sided limit, I can maybe say a little more. Maybe I can say which one it is. How do I figure that out? It's not something I'm going to do a basic transformation of. What do I do? So I can refine this form a little bit by saying a little more. Let's say here, more. The form is -1, sure. That's what the numerator is doing. But because it's a one-sided limit, x is approaching 2 from the left, meaning it's always a little less than 2. Remember, it never gets to 2. It's like 1.9, 1.99, and so on. Always a little less. So x minus 2, I don't want to say just 0. I want to say, is it a little positive or a little negative? It's never actually 0. It's just very close. So if I have my x values being a little less than 2, and I subtract a whole 2, what is my answer? 1.9 minus 2. Negative. 1.99 minus 2. Still negative. Smaller in size, yes, but a little negative. A little negative. And now I can see, well, the top one is approaching -1. Whether it's from the right or the left, it's -1. Negative 0.99, -1.1 is still negative. It's only an issue when I'm right around 0. Any other number? Well, that's the sign of the number, negative. So now I see that I have a negative number divided by another negative number, and therefore it is positive infinity. This was just for me. I don't need to write that. So being a one-sided limit, I can't always rely on my graph, right? It's not always an easy transformation, and it's going to take me a good few minutes to transform that guy because of the x plus 3 at the top, so I don't want to do that. I can look at the signs of the components and count how many negatives there are. Does that make sense? So plug in some numbers if that helps you to make sure that's a positive or a negative. Yes?
So before when we said plus or minus,
we didn't have one-sided limits yet. That was the problem.
okay, so
So you can go back technically. almost all of them, yeah. You can go back and update those. But if this wasn't a one-sided limit, if that wasn't there, then we can't say. Because this could be a positive or a negative, I don't know. It actually jumps between them, so I can't say anymore. But because I now specifically cut out half of it, I mean, this probably, I don't know off the top of my head. This has a vertical asymptote at 2. It's going to go this way. Probably like this. Doesn't really matter. If I had the original limit, then different things are happening, I can't say. But if the question gives me a one-sided limit, now I'm only looking at that side. The other half doesn't even exist. And I can be a little bit more specific. But it does not exist either way. It doesn't exist. None of these exist. It's just I want to give as much information as I can, because maybe I'm analyzing this function, and this is just one small part of a larger question. So I want to ideally say as much as I can. If we now look at 11 itself, limit x approaches 2 from the left, x minus 3, x plus 2. Don't be deceived. Not every limit question is on the edge or near a problem. Where is the problem x value for that rational function? Where the only place where a limit could not exist. Where is the problem for that function? We just did it. It's the same function. Where was the problem? It's minus 2. X equal to minus 2. That's the problem. These cannot be hard questions, people. This course is going to be the bad news if we can't look at that function and immediately see it's minus 2. But that's not the x value that this limit is asking for. This limit is asking for 2. What's the form of this limit? What does x minus 3 do when x approaches 2? Minus 1. What does x plus 2 do?
What?
X goes to 2. X plus 2. 4. There's no 0 anywhere in that. The answer is negative 1. Yeah, negative 1 over 4 exists. No problem at all. The form tells me much more. I don't know why every book should use and make a clear explanation of how to use the form of a limit. They don't. I guarantee you the textbook doesn't have those words in there at all. And it says so much I don't understand. It tells me exactly what the answer is. And if there's a 0 somewhere in the form of the limit, it also tells me how to proceed. Do I watch out? It tells me everything almost. 0 over 0, sure, then I have to work a little bit. But it still gives me a lot of information. There's no 0 anywhere. There's no issue at all. The fact that this was a one-sided limit is completely irrelevant. There's no issue at all. Because if I have a graph, now we have a rough idea of what this looks like. You don't have to know at this stage why I'm coming at it from. 2. Oh, sorry, I changed, the function changed. This guy's going to sit over here. Probably the same. Oop, let me graph this some more. That's very wobbly. Seriously, do your job. I'm just thinking, what's the y-intercept? It's negative, so okay. So I'm coming at it slower. Okay. It's asking for over here. Zoom in. Whether I'm walking from both sides, whether I'm walking just from the left, there's no issue there. Oh, did I not do that right? Oh, I'm way slower than that, I'm sorry. The growth is much, much slower. And there's 2 over there. Still doesn't matter. A one-sided limit doesn't matter if there's no issue in the graph. I can come at it from both sides, just one side, don't care. The answer doesn't change. And the form can highlight that very well. I'm graphing these extremely fast. Don't look at my wobbly graphs too much. I'm just trying to position the point. The form is just so awesome. I don't know why. I do it every time, especially in the case of a rational function. It's really where it is the most useful. And it tells me exactly that's the answer. If there's no zero in this form, that's the answer. All right, let's do another one. I like number 8. We can't hide from the square roots for very long. X goes to -7 from the right. Square root of 1 over. Whew, maybe I should have eased into this one. Oh well, it's written down. Can't erase it. Well, I can't. I don't want to. Just do it. Okay, so my steps are essentially the same. My first step is look at that function. What do I see? I see a square root, and inside the square root is a rational function. So there are multiple aspects to this that I need to watch out for. Okay, and if I didn't have a one-sided limit, then I need to check where am I inside the square root. Am I close to the square root of 0? But I have a one-sided limit. I can still check that, I suppose. And you can look at the form still. Absolutely. It's just not as consistent if I have other functions around it. And I'll write the form like this, 1 over. You're not calculating anything necessarily. You're not solving for much. You're just isolating the pieces. And there's a square root that's still there. The 1 stays 1, sure. X plus 7. X plus 7. When x approaches -7. Well, in general, if x approaches -7, x plus 7 is going to go to 0. But I have one side of it, so I need to keep track of how I'm coming towards that 0, positive or negative. So if x is getting close to -7, but it's always a little more, like -6.9, -6.99, that's a little more. Doesn't mean it's positive, just on the high side, on the right side of -7. Then I add 7. Do I get a positive or a negative? Feel free to use your calculator, play with numbers, whatever works for you. It's a positive number. I don't have a calculator with me. Okay, everyone happy with that sort of breakdown of the pieces, how they behave individually? You cannot, let me just play this again. This is not saying you should plug into your calculator square root 1 divided by 0. You're going to get an error. And you can't then assume it's one infinity or another. I have to look at the pieces. In this case, I have something that is a square root, okay? Inside the square root is something that does what? Well, they're always positive. All the pieces are positive. And the numerator is non-zero. The denominator only shrinks down to 0. So inside the square root is what? What's the behavior? Positive infinity. So now I'm asking for the square root of something that keeps growing and is positive. Well, I can visualize my square root function for sure. That does help me. These basic functions I did for a reason. Now I'm not going to call this x. Let me just backtrack. I'm not going to call it x. I'll call it the inside, because x is something else. This is not the function, right? I'm just looking at the square root function and its behavior. This is the inside. The inside approaches positive infinity. I can't see my eye there. So in a square root where the inside keeps growing, what does the answer do? Positive infinity. It keeps going up. So positive infinity. Does that limit exist? No. It feels as if, oh, but I wrote an equal. No, that's just, the equal sign is extremely unfortunate, I agree. Because infinity is not a number. That equal sign shouldn't be an equal sign, but everyone writes it like that, understanding that if it's an infinity, it still doesn't exist. We're just giving more information. All right. So the one-sided limit helps me to be a little bit more specific. If that wasn't the one-sided limit, if that was a two-sided limit, then I can't say any of it. Because I'm not sure about this plus anymore. This is only due to the one-sided limit. If I can't say that plus, then this could be around zero, negative or positive, and I can't evaluate negative numbers. So I can't say this, but I can still say does not exist, but for a different reason, because sometimes inside the square root there are negative numbers. And then it's an immediate, nope, nothing works. Question makes no sense. Does not exist. So does not exist is vague. It can come from multiple places. And I want to know, why doesn't it exist? Because in this case, it has stable, predictable growth, but it doesn't approach a specific number. That's why. That's not really a terrible thing, but it is a specific kind of behavior. Any thoughts so far? Any thoughts so far? Does it make sense? Sort of? See how very often, every other question almost, there's a basic function. Or one transformation of it. I'm not wasting your time with anything. Yes?
So if you divide 1 over 0 inside the square root, it would be positive and negative infinity does not exist.
So, because I can't evaluate the square root for the negative bunch of those numbers. So that means I can't, there's only one side, right? I can't evaluate an inside that is the negative side of it. And because of that lack of available behavior to check, the question makes no sense. The question is sort of thrown out. If I have a two-sided limit, I need to be able to evaluate numbers coming in from both sides. And because of the square root, I can't have any negative numbers in there. So I cannot evaluate anything, technically. And I just stop and say, nope, makes no sense. And it's really only going to happen with square roots. So we do have another layer, admittedly. We have to check what kind of limit am I looking at, especially in the case of square roots. Because if I have a two-sided limit and I'm on the edge and things are happening inside that are negative, then I can't. I have to stop. Makes no sense. It's undefined. But if I have a one-sided limit, then I have a better chance, but I still need to check what's happening inside. So I do need to, the first thing I need to do if you want to update your strategy list and steps and options, the very first thing is be aware of what kind of limit. I would say that is the very first strategy. Oops. Let's update our strategy. First thing to do is be aware of the type of limit. Be aware of the type of limit. All right, let's talk about a little absolute value function. I'm not going to do a lot with absolute values, but we do need to look at it. Let me just not even worry about a limit. I'm just going to look at the function, the absolute value function. Is it done? Who knows? Okay, no follow-up question. Because I think people are afraid to answer yes or no, because then they think I'm going to ask them for the next part, which is, what is it? No follow-up question. Do you know what the graph of that function looks like? New question, not a follow-up, separate question. Should you know what the graph of that function looks like? Yeah, you should. Yeah. I don't give it as much importance to include in our basic functions. It's not one of our basic functions that we're going to transform or anything. So it's less important, yes. And you're not going to see it that often. Can you pass the course without knowing what the absolute value function is? Yeah, you can. Yeah. It's not a deal breaker. But it comes up in little things. Can you get 100%? Nah, probably not. But you can get 90% easily. So. It's not super important. But it is used to illustrate something with two-sided limits because this isn't one function. This is really two pieces put together made to look like one function. It's not one function. This is two different functions. If x is greater than or equal to 0, and if x is negative. You can see the two straight lines are not the same thing. If x is greater than or equal to 0, so I'm looking at the right half, then it's the line y equals x. This is the line y equals x. And the other guy is the line y equals negative x. So I'm really putting two pieces together. And the reason why the absolute value is so annoying, I thought pre-calculus, it was super annoying. Did not like it. Because it makes you think it's one function, but it's really not. It's a piecewise function. And I need to treat it like a piecewise function. So if I look at the limit as x approaches 0 from the right of this function, what am I really asking for? I'm saying I don't care about negative numbers. They are dead to me. There is no left side of that function. I'm only looking at positive x values, which means I'm only in this case. Which means everywhere I see the absolute value of x, I can replace it with that piece, which is much simpler. It's just x. So as x approaches 0, x approaches 0. It exists. Which makes total sense. If I walk along the graph from the right, I'm going to a y value of 0. Okay, it's fine. It's not a complicated graph in its basic form. If I look at the limit as x approaches negative 0 from the left, which means negative numbers, this means I'm only looking at this case. I don't care about the other half. That's the benefit of one-sided limits. So I can replace the absolute value of x with negative x. But that still is going to approach 0, which makes sense because if I'm walking towards 0 from the other side, I'm still going to the same y value of 0. So I can now, in a sense, combine these two to say, well, the behavior as I'm walking towards x equal to 0 from either side is exactly the same. And I can say the limit as x approaches 0 of the original function, allowing both sides, is also 0. And what this tells me is, the following. It's going to be a little wordy, perhaps. If each one-sided limit exists and they are the same, they're equal to each other, like they are here, they're both 0, then the two-sided limit exists and is that same value. So in the case of a function that comes in pieces, and most of them are a little made up, with the exception of the absolute value, they do come up for our purposes. We don't really care too much about them in this course, but in the final exam, there's always that one question that some instructor loves, not me, but they always put in that one question, and it relies on that bottom sentence. And we're going to do a little example in the last couple of minutes. If I have something that's in pieces, I look at the behavior of those pieces, and if the behavior from both sides agree with each other, then the limit exists. The two-sided limit exists as well. But this also says that if it doesn't agree, then the two-sided limit doesn't exist. Let me show you an example. They're going to be very made up, because with the exception of the absolute value function and fancy applications, they don't really come up. Which is why you can pass the course without this knowledge. But let's make a graph that's weird and made up, but that's what the final exam question is probably going to be. Let's suppose I have a function here, maybe a little hole there, and then it continues, and maybe that point is at 2, and then here I have another piece, and it does like that. Yeah, sure. And the question is, what is the limit as x approaches 2? This is, of course, y equals f of x of this function. That's the question. Now, the one-sided limits really just give me the mathematical words to explain why this doesn't exist. But in plain English, if I walk from the right, let's suppose this is a y value of, let's say, 4, and this is a y value of 1, I can say, well, the limit, if I'm walking from the right, then x approaches 2 from the right of the function is 4. It exists. But the limit as x approaches 2 from the left is 1. Yeah, it also exists. If you ask me, where are you walking to? I'm walking to 4. Where am I walking to? 1. So they both exist, but they're not the same. They're not equal. Therefore, this does not exist. I can't walk from both sides and approach a specific y value. I'm going to 2 different places. So the one-sided limits just give me the language and the words to explain why that doesn't exist. But in plain English, if the pieces don't link up, there isn't stable behavior from both sides, even though individually they're perfectly fine. Just as a side note here, let's suppose this is -2, and this is let's say a 3. As a side note, does the limit as x approaches -2 of the function exist? There's a hole. The function's undefined. Does the limit exist? Because the limit is only asking for behavior, the fact that there is or isn't a y value is completely irrelevant. You walk along the graph towards -2. Are you approaching a specific y value? Yes. I'm approaching 3. I'll never get there, but I'm approaching it. People look at what's happening at that point way too much. It's completely irrelevant. Completely irrelevant. So the one-sided limits just give me a way to explain pieces linking up. But visually, if we understand the behavior question, we can see it visually as well.
Please remember to click the like button if you enjoyed the video, and to subscribe if you want to be notified of more videos. Thank you.